Hello, it's still morning, so causal inference morning. So before we break for lunch, we're going to hear from Naz, studying at Tilburg University as a researcher. So she's going to talk about staggered diff and diff in practice. So without further ado, please give a warm welcome to Naz.
Yeah, thank you very much. Yes. Hi, everyone. Thanks, first of all, for joining. Today, I will talk about difference and differences, situations where it may not work if you use it in a regular fashion, and I'll use a motivating example from music industry. Before we get started, I want to know who is familiar with difference and differences? Okay, quite a bit. And have you applied difference and differences yourself? Yeah, some people. Okay, well, we have a variety of people, a variety of familiarity, but I think everyone will be able to take away something from this presentation. Before I get into the topic, let me introduce myself a little bit. You can call me Naz. I'm a PhD candidate in quantitative economics at Tilburg University, and I have a background in economics and econometrics. I'll be graduating soon, so if you are interested in my stuff or your company is interested, I will be happy to talk after my presentation. Yeah, so everyone got the point? Yeah, let's get started. Oh. Right, so as a researcher, I was interested in kind of investigating economics in music industry, and lately, in the recent times, we came across this song by Kate Bush called Running Up That Hill. So this song was originally released in 1980s, but I am sure a lot of you and a lot of people in the world have heard this song for the first time in the recent few years. And this was because this song was featured in a popular Netflix show called Stranger Things, like 2 years ago. And from there, this song just got a huge boost in popularity, and it's reached #1 in many music charts about 40 years after its original release. So we observed this, and we also observed similar examples of like songs being featured in TV series or movies and getting just a huge boost in popularity. And as I am in marketing, I asked, okay, can we use this, or can the managers in music industry use this featuring as a promotion tool? In the music industry, these are called music synchronizations. So these are whenever a song is featured in movies or TV shows. And in the music industry, there are some very successful examples like this Kate Bush example that got really a huge boost. But it could also be that this song and a few other successful examples are rather outliers and not the rule. So from this example, I wanted to investigate what is the impact of music sync on song popularity on average. And if I didn't know about difference and differences, or in an ideal world rather, in an ideal world, what I will do is choose some random songs and assign these random songs to be featured in some TV series, and choose some random songs not to be featured so that they will be my controls. But in this case, A/B testing is not feasible. As you can imagine, it will be really hard for me to go up to the TV show runners and say, here I choose some random songs for you. Why don't you use these in your TV show? It's just not possible. So the next best alternative is to use observational data, as Kevin kind of talked about, the previous speaker. What I can do is I had a data set that had songs that are synced in TV shows and that are not synced. So basically, the idea will be to kind of, in a way, compare these. And I had done some outcome metric that kind of reflects popularity. We had the number of playlist placements for like Spotify playlist placements for all of these songs on a weekly basis. So the idea is that the more popular a song is, the more playlists it is in. And of course, I did some checks to kind of see if this is actually reflecting popularity, and it was a very reasonable kind of outcome, and it was kind of the best kind of outcome metric that we could use. And how would I kind of answer this question, what is the impact of music synchronization on popularity? If I didn't know about differences, first idea that would come to my mind is to just compare the outcomes for synced versus unsynced songs. But imagine like songs like Kate Bush, Running Up That Hill, they are inherently different from songs that are not synced. Once I kind of checked out the summary statistics comparing synced versus unsynced songs, I realized, as expected, synced songs are different from the unsynced ones. Usually they are way more popular from the start, and there could be many other like song level characteristics that could be different. So if I just compare these two groups, I will be ignoring song level differences, and that could lead to biases in my estimation of the impact of synchronization. The next idea could be, okay, if the unsynced songs are not good comparison, they are different, why don't I just compare before and after of the synced songs? The problem with this is that it ignores any time trends that might be happening like across all the songs. Maybe all of the songs are decreasing in popularity, or it could be like there could be some seasonality. For example, at the end of the year, Christmas time, Mariah Carey's song, All I Want You for Christmas, that really gets a boost in all of the platforms, and also it is usually synced more. So you will be kind of, if you try to estimate using this comparison, you will be confounding the effect of sync with seasonality. What is the solution? That's the difference and differences. So difference and differences takes both of these things into account, and kind of under certain conditions, it gives you a good estimation of the treatment effect. In this case, the sync. Let's get into how this difference and differences estimator works. So I put a very simple example. This is 2-group and 2-period case. So I have 2 groups here, represented by these 2 songs. So Running Up That Hill is the treatment. As you can see, the T sign over there. And Tarzan Boy is another song, and this is not synced, and it is a control. As you can see, Running Up That Hill is synced in the second period for Stranger Things. Meanwhile, Tarzan is never synced. So that will be my control. And let's see how difference and differences estimator works. Let's say popularity of Running Up That Hill was 2 units, just imaginary popularity unit. And after the sync, it got boosted to 5, right? First, a difference and difference estimator takes this difference, so the change is 3 for this song, the treated song. And I will do the same for Tarzan Boy, the control. So the popularity increases from 1 to 2. And the change here is 1. And what this estimator does is to basically compare the amount of changes in treatment versus the control. In this case, it will be 3 minus 1. 2 units of change can be attributable to the sync in this case. Just to mention, a core assumption in all of the difference and differences methods is parallel trans assumption. I'm using that assumption here, assuming that the change for Running Up That Hill would be 1 if it was not synced. So this is an important assumption, but it's not the focal point of today, but it's something to keep in mind always if you are using difference and differences. Right, so I think we get the basic working of difference and differences. But the thing is, the data I had with a lot of songs, many songs, thousands, I didn't have just 2 groups. My data looked more like this. So I had more than 2 groups, so songs getting treated at different times, and yeah, multiple time periods. So in this case, I have a simple case, 3 groups and 3 time periods. So in the first case, what we have here is, again, running up that hill song, and it gets synced in the second period. So that's the early treated group. And surf time, as you can see, is the late treated group. Tarzan Boy is never treated. And you might ask, how does a difference and differences estimator will work in this case? Because I don't have, it's not as simple as before. But what the econometricians found this estimator does in this situation is that it takes a weighted average of 2 group and 2 period combination estimates. What do I mean by this? I'll come to that. But I hope, this is the kind of the situation we have. How do we go by kind of estimating the treatment effect? As I said, it is 2 by 2. So the DID estimator will look at the 2 by 2 combinations where there's some sort of a status change in terms of the treatment status. So the first case will be this. So the first component of the weighted average. That will be, running up that hill will play the treatment here, and surf time will play the control. Next component in the weighted average is this one, pretty similar. There's not much changing. And you will just calculate the estimated treatment effect as in the first one, and use that as the component in your weighted average. And then later, I will look at the last 2 periods and 2 of the different groups. Here, surf time plays the treatment, Tarzan Boy is the control. It was good so far, but it appears this estimator also uses this combination as one of the kind of combinations in the treatment effect estimate. So what we have here is running up that hill. It is already treated, so it was treated in the between first and second period, but it plays the role of control here because there's no status change for this one. Meanwhile, surf time, who's the song that is later treated, it plays the treated group for this estimator. First thing to realize from here is that this comparison is not very intuitive. Why would you use early treated song as a control? But it can be, and that's why this is called forbidden comparisons, and it will cause some problems, and I will show you how. So let's say, running up that hill, got some initial boost from the sync. But later, it even, things picked up. So the popularity went from 5 to 10 in the second kind of the exposure period, exposure to treatment. So the difference I would calculate from this is 5. And the 5 is the change for the control in this situation. And this second case, so the surf time, the actual kind of treatment playing a song here, the popularity increase was not as strong for this song. So there's some heterogeneity. So there are differences between groups. And the popularity went from 2 to 3, so the difference is 1. And if I compare the change in treatment to the control, so 1 minus 5, that is equal to minus 4. So that will be kind of the component, the last component of your weighted average that will go into kind of estimating this treatment effect with difference and differences estimator. As you can imagine, the kind of the issues that this could cause, even though in all the cases, the synchronization had a positive impact, and here too, but it is giving us a negative estimate. So in kind of, if this heterogeneity is really high levels and, in certain situations, if you do not account for this variation in treatment timing, and if you do not prevent this forbidden comparisons, you might end up with really biased estimations of the treatment. Right, so we understand the problem, but thankfully, there are also some solutions. So as we have seen, traditional difference and differences estimator might lead to misleading estimates in the cases where there's variation in treatment timing and also like high heterogeneity between groups in terms of the treatment effects. And this is because forbidden comparison, so when you use early treated group as the control, what we can do to kind of address this issue, use clean controls. So we can use the unaffected, the units and time periods that are unaffected from the treatment. And there are a few methods that are developed to kind of address this. There are many methods, but I think these are the most commonly used, and they are kind of, I think, the most flexible. Staggered difference and differences by Callaway and Santana, and stacked difference and differences by Cengiz et al. So I'll shortly explain this to just give you an overview of these methods. First, staggered difference and differences by Callaway and Santana. So the practical implementation of this is that this method calculates the treatment effect, estimates the treatment effects for each of the group and time periods. And then you can aggregate this to a group level or exposure to the treatment or an overall level. In terms of the advantages, this method has a R package called DiD, and it has a very transparent selection of control groups, so that's very nice. You can see exactly which units and time periods are used as controls, and it has a lot of like customization ability. The disadvantage is that, for example, in my example, if you want to kind of learn how does the effect of sync changes by song age, like do older songs benefit more from the syncs, for example, maybe because they evoke nostalgia. You can't do that with this method for now. There's no way to kind of measure heterogeneity in the treatment effect along some covariates. You can do it at the group level, etc., but or cohort, and it can be also computationally intensive. So that's the downside. But it's pretty good place to start. The other option, in my opinion, is to use stacked difference and differences. How does this work? So initially you create a group-specific, so treatment group-specific data set, and you kind of include clean controls in these little data sets. Later you stack these data sets on top of each other, and you create this stacked data and run a modified difference and differences analysis for this data. In terms of the advantages, it is pretty similar to traditional difference and differences kind of approach, but it's a modified version of this basically, where you choose the controls. It is computationally inexpensive compared to the previous one, and can include covariates to investigate heterogeneity in the different groups. The disadvantage is that there's no package for its implementation, but you can kind of search up some sample code on GitHub. So it's not too bad. So let's tie in everything together. What happened to my, what is my results from trying to answer this question? Does sync have an impact on music popularity? So I kind of graphed my results estimations here. On the x-axis, I have weeks since the synchronization, and minus numbers are for before the synchronization. 0 indicates the week of synchronization, and I graphed it until 4 weeks after the synchronization. I have the estimates, so these are, I kind of did this, the outcome is a log number of playlists a song is placed in. And this basically estimates show the change in the number of playlists a song is kind of placed in. As you can, so I graphed all of the 3 kind of approaches, Callaway and Santana, stacked difference and differences, and traditional one. In my case, so overall, as you might realize, the first thing, for me, it doesn't make much of a difference. So, but it is always good to check. It could have been big differences. In my case, it doesn't. So what I see here, if we start from the minus period, I don't see any particular different trends in the outcome for synchronized songs, and the same is true for the after the sync. There are some kind of difference between in the week 0 Callaway-Centeno method and the rest, but that can happen because these, compared to the stacked, these methods are similar but not exactly the same, so there are kind of the minor differences can happen. So overall, the answer is that no, on average, the synchronizations do not benefit the songs, but the next step in this case for me will be to look at different groups. Is it affecting, for example, older songs better? But these are the answers. So what are the takeaways? So difference and differences can be a powerful tool in situations where experimentation is not practical. But if there is a variation in treatment timing, the traditional difference and differences estimator might lead to misleading estimates. And we can avoid this by using right approaches that account for this variation in the treatment and uses the right controls. So that was my talk. Thank you very much for listening. And you can find my kind of more writings, blogs on this on Medium. And yeah, I will be happy to talk to you if kind of you are interested in this stuff. Yeah, thank you. Oh.